Moving on to another geometric application of integrals, we're going to find how to calculate the arc length of a curve. So if we have a curve like the one I've drawn here, some function f of x, and we want to find the distance between a and b along this curve, you can imagine like driving along a road. As you travel from a to b along this curve, how far do you travel? So the arc length is just the distance, if you imagine a string that we could lay along this arc along the curve, and the length of that string would be the distance between the two. So it turns out for a general function like this, we need some calculus to do this. For simple geometric figures, like if this was a perfect circular arc or elliptical, maybe we could find formulas to do this for us, but for a general function we need some calculus, we need an integral to do it. And we're going to derive the formula here in this video to calculate the arc length between 2 points. Now the formula will look a little bit complicated at first, and it turns out that we can't do this manually for a lot of functions. The functions need to be fairly simple for us to be able to calculate the integral by hand, but there are some that we can use a calculator for, and I'll show you in a later example how to do that in a more general sense. So as we think about how to calculate this arc length, we're going to step back to how we do things with integrals in general, where we start by approximating the thing we want to find. Back when we first encountered integrals, we approximated the area under a curve using rectangles, because rectangles are easy to work with. And then with volumes, we start by approximating with slices and integrating from there. The same thing will hold here. We want to approximate this length using a simpler length that we know how to calculate. So let's start by saying, what if we just looked at the straight line connecting A and B, and we found the length of that line? Now you should know how to find the length of a line segment. That's going to be depending on the x distance and the y distance. We could think about this on a large scale. If this distance is x and this distance is y, we have a right triangle, so we can set up the Pythagorean theorem, x squared plus y squared equals L squared. And then the length of L would just be the square root of x squared plus y squared. And of course it's the positive square root because length is a positive value. So in general, you should remember this sort of thing because we'll use that, and that'll be part of our derivation for the formula. So let me erase what I've drawn with x and y here, but keep that in mind that the length of this straight line between the two depends on the horizontal and vertical distances, and then if you square them and add them together and take the square root, that's the length of that line segment. Okay, so we could find the length of that line segment. Would that be the same as the arc length? Of course not. But would it be a decent approximation? It would at least get us in the right ballpark, right? So how would we make this better? Think back again to what we did with areas, with one rectangle to represent the approximate area. It wasn't very good, but if you split it into 2 or 3 or 4 or more, it started to get better and better. If we split this into 2 steps, for instance, by picking a point kind of halfway in between A and B, we could draw one line segment from A to this intermediate point, and another from the intermediate point on to B. And that's a much better approximation. If we added those two together, we're getting closer to the actual arc length. Now you can apply your calculus sense to this and imagine drawing many, many points along here where we approximate this with lots of tiny line segments. And the more line segments you draw, the closer it is to that true arc length. And then you can imagine taking a limit as the distance between those intermediate points shrinks to nothing. It becomes a truly perfect line that follows that arc and gives us the perfect arc length. So we're going to zoom in and think about one little slice and how to find the length of that and use that to build up to this full picture. So zooming in on one little section of the curve, we're going to have a line segment approximating that segment. And we'll have the length of that little section where we can, as we did before, talk about the horizontal distance and the vertical distance. So maybe we can call these the run and the rise like we've done before. And the length is going to be the square root of the rise squared plus the run squared. Just like we saw earlier, because of the Pythagorean theorem, this little right triangle works out to give us the length this way. So then the run and the rise, like we've seen before, even in your algebra classes, this is the difference in two x values, and the rise is the difference in two y values. So we can think of this as delta x, and this is delta y. A small x distance and a small y distance. So this length of one little segment would be the square root of delta y squared plus delta x squared, or I'll write it in this order, delta x squared plus delta y squared. Now again, remember we're building to a formula, so if the intermediate steps don't make complete sense, that's okay. I just want to show you where the formula comes from so that at least you've seen it once. Now we'll do a little bit of tricky algebra where we're going to factor out a delta x squared. Now you may notice that when we do this, the second term doesn't have a delta x squared. But if we do this little trick, it all works out. If we divide that by delta x squared as we factor it out, now those two lines are equal. And you can double check the algebra if you prefer, but if not, we'll move forward. So now if we take the square root of these two pieces individually, the square root of delta x squared is just delta x, and then we have the square root of all of this, and I can rewrite delta y squared over delta x squared as delta y over delta x all squared. Now imagine making this line segment smaller and smaller and smaller, shorter and shorter. So we take the limit as delta x and delta y go to 0. That's what happens as we make this line segment infinitesimally shorter. So this turns into the square root of 1 plus dy over dx squared, and then dx on the outside. So it turns out that the full length of the arc, we'll call this L, is the integral from the beginning to the end of the square root of 1 plus dy dx squared dx. Or we could write it as the integral of the square root of 1 plus f prime of x squared dx. Now you can kind of see how the function f of x needs to be a fairly simple one for us to be able to integrate this, because inside the formula we have the square root of something squared. So if that function is too complicated, it's going to be one we can't really do by hand. But we can always use a calculator if we need to, at least on the homework. But recognize that the derivative is on the inside of this function. That's one of the parts that trips people up a lot of times. They just plug f of x in instead of f prime of x. But as long as you apply the formula carefully, it's not too hard. The a and b, of course, are bounds in terms of x. That would be the x value at the starting point and the x value at the ending point. So there's the formula, and we'll do a couple examples in the next video showing how to apply this formula.